So in this video, I want to go over an important concept having to do with acid-base neutralizations, and that is when you've done the complete neutralization. Another way of saying that is when you're at the equivalence point. If you were to do a titration where you're doing the pH curve, you would have essentially an aqueous solution of the salt of the neutralization reaction. All right. So the thing about this is, if we wanted to determine what the pH is at the equivalence point, basically what we're doing is figuring out what would the pH be of that salt. All right. So as an example of this, let's take a look at this particular example. Let's say that we're going to be doing the neutralization of 100 milliliters of a 1.0 molar solution of acetic acid with a 1.0 molar sodium hydroxide solution. All right. So first of all, some things that we're going to have to know: acetic acid. Acetic acid is also known as ethanoic acid. It's more commonly called acetic acid, though. So here's its formula right here, and some information that we're going to need to know about it. If you look in the data booklet, you'd see that its pKa is 4.76. Hopefully you realize by now, once you have the pKa, you can calculate the Ka from that, and that's going to be useful in a lot of these reactions. All right. So let's start off by writing an acid-base neutralization reaction. All right. If you want to, you can pause the video. Make sure that you can do this yourself. All right. So think about what would you make if you reacted acetic acid with sodium hydroxide. All right. Hopefully you'd realize that you would get the salt, which is sodium acetate, and you would get a molecule of water. All right. So when we're at the equivalence point, what are we going to have? All right. So remember, so actually let's go ahead and take a look at the pH curve. All right. So so first of all, some things about pH curve. Remember, this is starting with a weak acid, so your starting pH is going to be not going to be extremely low. It's going to be below 7 because it is still acidic. All right, we're going to go through this region right here. Remember, we call this the buffer region. All right, and then you're going to get this sharp increase, and at that inflection point, that's the equivalence point. All right, so that equivalence point is the point where we've added exactly 1 unit of this for every 1 unit of this to make 1 unit of this. All right, so we can figure out how much that would be. If we were to have this much total of the acetic acid, we could do the calculation to figure out how many moles that would be. It would be this many moles. Therefore, to fully neutralize it, since it's a 1-to-1 ratio, we would need 0.1 mole of that. All right, and when we add these two amounts, we would have exactly 0.1 mole of the sodium acetate. All right. So what I wanted to point out is that when you're done, this is what you would have here. All right. And so the interesting thing about this is, if you were to take what's left in the solution when you're done with the neutralization and just sit it out and let it evaporate, all right, you would essentially have pure solid sodium acetate. All right. So just to give you a little feel for what that means, sodium acetate is it's a common chemical. You can buy it. All right. So it would be a white solid powder. It's actually not that harmful, and it's going to be slightly basic. All right. And the reason that it's going to be slightly basic is that it contains acetate, which, if you look back at this reaction right here, so this is the acetate part. All right. So that is the conjugate base of a weak acid, and so it would be a weak base. All right. So a way of thinking about how to do figure out what the pH would be at the equivalence point is just to say, what would the pH be of this solution right here? All right. So how are we going to do that? Right. So as I said before, at the equivalence point, you would have 0.10 moles of sodium acetate dissolved in 200 milliliters of solution. All right. So how do we get those values? First of all, the 0.1 moles comes from this little bit of stoichiometry, And the volume of the solution we can determine because we started with 100 milliliters of our acid solution, and since they're both the same molarity, we know that we would also have to add exactly 100 milliliters of the base solution to fully neutralize it. All right. So if we take that 100 milliliters and we add the 100 milliliters of the base that we had to add, that would be a total of 200 milliliters. All right. And from that, we could calculate the concentration of the sodium acetate that's in the neutralization solution. All right. So we would have 0.1 moles of acetate. All right. So again, if we have 0.1 moles of sodium acetate, remember when this is dissolved, this is an ionic compound, we would have 1 sodium for every one of these. So we would have 0.10 moles of the acetate. So that's what we have here. All right. And 200 milliliters is the same thing as 0.2 liters. All right. And we can do the math on that, figure out that solution that we have when we're done with our neutralization is going to be essentially 0.50 molar in acetate. All right. That's the conjugate base. That is the conjugate base right here of the acetic acid, which would be swimming around in that solution. All right. So essentially, this problem becomes the following. All right. If this is in water, it's going to act as a weak base. All right. So it's going to have an ability to react with water to make some of the acetic acid plus hydroxide. All right. So this is classical weak base reaction. And so what do we need to know about this? All right. So hopefully you remember, if we know what the Kb is, the base dissociation constant, we could figure out eventually what the concentration of hydroxide is, and eventually get to the pH. All right. So first of all, how did I know that this right here was the Kb of the of acetate? Okay, so there's actually two ways. First of all, I'm going to start by saying it has something to do with this right here. All right, and again, this data was available from the data booklet. All right, so if you want to pause the video, see if you can figure out how we could get from that information to getting this Kb right here. All right. So if you're stumped on that, let me just point out that there's two ways you can do that. All right. First of all, we have this reaction, this relationship right here. So at room temperature, we know that the Ka of an acid times the Kb of its conjugate base is 10 to the minus 14th. All right. So we could calculate the Ka of acetic acid from this pKa and plug it in here and eventually get to this Kb, since this is the conjugate base of this acid right here. All right, but there's another way that you can do this. The pKa plus the pKb is going to equal 14. All right, this is kind of similar to the pH plus the pOH always equal 14. So if you say 14 minus this, you'll get some number, and that would be the pKb, and then we could calculate the Kb from the pKb. Either way, you end up getting this value right here. All right, so what are we going to do with that? All right, well, we're going to set up the same classic start, change, finish, or final state type of calculation. All right, so we know that the molarity of our at the start would be 0.50 molar. That's what we calculated here. And we would have 0 of these guys. This is all 1-to-1 coefficients, so we could say you would lose a certain number of moles of this, all right? And you would be adding the same number of moles of this, all right? So since when we're doing this, we're assuming that we're doing this in 1 liter. It's once you get to molarity, you can just assume that you're doing it on a 1 liter solution, and it simplifies things. All right. So So if we do this, this would be our final concentration of acetate. X and X would be our final concentrations of these. And we could treat this the way we've done base problems in the past. All right. We know that the Kb would equal this expression right here. You can get that from this equation right here. And plugging in what those values would be, we could get to this part right here. Again, this right here, remember that we've assumed that since this is a weak base, that the 0.5 minus x is essentially the same as 0.5. All right, we have x squared in the top. We are eventually able to calculate our hydroxide concentration. That would then allow us to calculate a POH, and from the POH we could calculate a pH. All right. So one thing I want to point out about this particular problem is that, all right, the solution at the equivalence point would be essentially identical to a solution made by adding 0.1 moles of sodium acetate to a flask and adding enough water to make 200 milliliters of total volume. All right. So what that means is if I take 100 milliliters of this solution and I mix it with 100 milliliters of this, all right, remember this is essentially like vinegar and this is essentially like it's a strong base. What we would have is essentially the exact same thing, all right, as if we took this solid salt right here and we took 0.1 moles of that and we dissolved it in 200 milliliters of water. All right. If you think about it, that's exactly the same thing that you would have here. All right. So hopefully that makes sense. And in the next video, I'm going to do a couple of practice problems where we are going to apply that.